Huntsville, Space Library DPM.
Go ahead, Kathy.
If you see a translation that you can live with, let me know and I'll quit working on it.
As you can see, this is like autoclave number 2, very similar. Population of very small, what I suspect are gel particles, a couple of bubbles mixed in, and I don't believe there's any zeolites there at this time. Let's switch to glove box camera, Dave. Microscope camera.
Copy that. Space Lab Huntsville for Al, we're receiving the microscope view now.
As you can see, we've got a uniform population of what I suspect are gel particles, a couple of bubbles, and I think that's about it. Copy that. You can see number 7 is a gel. We don't really need to switch to something else. 8 is also a gel, less viscous. 10 and 9 are gels. 11 is still a gel, and 12 is still a gel, and they all look pretty much the same and pretty much like this one.
Copy that.
Okay, Al. The pictures that you sent back and the last run show us that the crystallites are much bigger and better than we expected, and the Bragg scattering that we're getting is saturating the screen, so we can't get a good reading of what the crystal structure is. So the idea is to do a run again of some of the old samples with a lower aperture setting, and also to try and homogenize the samples and get smaller crystallites for comparison for what we get on the ground. That's why we want to do, why we changed the procedures so we can do the samples that we've already run again. We also want to see whether they've annealed and grown bigger and things like that, because they've just grown much better than we expected. That's essentially the rationale, and since the crystallites are much bigger, we think we can get away with a shorter run for the averaging for the Bragg scattering.
Sounds good to me, and it's nice to hear that you're getting something unexpected but on a positive vein.
Copy. They're beautiful pictures and beautiful crystals.
And I'd like a question on the homogenization procedure.
We are now receiving live video downlink from inside the glove box facility. The colloidal disorder order transition experiment, or CDOT, is being performed in this glove box facility at the moment. Earlier in the mission, this experiment was set up, and at various times throughout the mission, crew members set up cameras in the glove box facility in order to view the progress of the crystals that are growing in this colloidal solution. We are now receiving live video downlink looking at the top view of the drop physics module chamber. The experiment team on the ground has the capability to view both of these experiment cameras simultaneously due to the high-packed digital television technology demonstration. The direction of the force being applied to the drop is from the top and the bottom. This causes the drop to be squeezed or compressed in the center and causes the drop to elongate in a horizontal direction. If you look at the top view of this drop on the left side of the screen, you can see that there is very little change in the dimensions of the drop looking at the top. However, from the side, looking from the side or the right-hand view, the drop continues to be compressed from the top and bottom directions, or the vertical direction, as Kathy Thornton continues to increase the strength of the acoustic force that is compressing this drop. The width of the drop continues to become larger and the height continues to decrease. The experiment team for this experiment is looking
6.72 now, I'm still going.
We are receiving live video downlink from a Bragg camera that is located in the glove box facility. This is used on the colloidal disorder order transition experiment. This is an experiment that looks at glass spheres to look at how liquids form solids. These glass spheres are used because the forces that act on these glass spheres are very simple, and they can be used to model other materials that would be composed of atoms. These atoms would have a much more complicated force acting upon these atoms, and therefore the interaction of the liquid and the solid would be much more difficult to understand. So they use these glass spheres in order to look at the transition that these glass spheres go through when they change from a liquid state to a solid state.
The equipment seen here is part of an apparatus designed to help meet the needs of growing food and plant items in space. Right now we're looking at some footage of a potato plant being grown aboard the Space Shuttle Columbia right now. The special systems built into the astroculture equipment include systems for the delivery of nutrients to the plants. The modes for fluid flow and fluid delivery to the plants are different in the microgravity environment of space, and the astroculture team has developed specialized equipment to help feed and water the potato plant we see growing here. Additionally, they have developed subsystems which provide for the control of the humidity or the level of water in the air around the plant. And also they've developed some special lighting systems which are very low power consumption lighting systems so that they're very efficient for use in the spacecraft environment.
Huntsville, Columbia.
It's Huntsville, go ahead.
Hey Angie, it's Mike L.A. Good morning. Listen, I was wondering if we could get a head start on PAO event setup and be able to reconfigure some of the switches down here with the VAS.
Stand by, LA, and I'll check for you and let you know.
Okay.
And payload specialist Fred Leslie is taking a brief exercise break before his shift will begin in a short while.
Hotel Columbia. To be more specific, what I wanted to do was take your DPM2 source from the Orbital 1/HIPAC2 channel, so I could use the Orbital 1 channel for something else.
Copy that, LA, and that'll be fine. You can go ahead and do that.